Hello. In the last video, we looked at this example for a cubic function, and we saw where the roots were. And what we noticed was that the pattern of each term being positive or negative when you multiply them together, that pattern applies to all of the x values in the entire interval. Because the only time one of these pieces can change from being positive to negative, or vice versa, is when the x value you're plugging in crosses the root that involves that term. So for example, when x is, so here this term produces the root x equals 4. When x is smaller than 4, this term is positive. When x is larger than 4, this term is negative. Meanwhile, all of these other terms over here don't change. If they were positive before, they keep being positive. So that way of thinking can let you sketch a graph, because all you do is find the roots, and then between any two of them, you figure out what the pattern of positives and negatives are. And then you know that if the output is less than 0 or bigger than 0, it's going to be true for that entire region between the roots. And then I defined the term critical value, and I said 1 and 2 and 4 are the critical values here, because they're the places where the function might change from being positive to negative or back. In this picture, they actually do change from being positive to negative in all three. But think about what would happen if I did this instead. So here, this equation is what? 14. So this is a 16th degree equation. If I was going to multiply all of this out, I'd have, something times x to the 16th plus something times x to the 15th, and so on. But we know what its roots are. Its roots are still just 1, 2, and 4. This problem is pretty much exactly the same as the last one in how you can think about it. Except now, notice that it doesn't matter what x value I plug in for x minus 1. If it's positive, I raise it to the 10th power and it's positive. If it's negative, I raise it to the 10th power and it becomes positive. So because all of these exponents are even, that means whatever I plug in is going to get raised to an even power, and so it's going to become positive. So now I don't even need to plug in different numbers in different regions. I know that for all possible numbers, I've got a positive output for my f function, because it'll be a positive number times a positive times a positive. So what does the graph look like? I know that the graph still needs to hit y equals 0 at the roots. Like when I plug in x equals 1, I still get 0 times some positive numbers is 0. But what you're going to end up getting is a graph that dips down to 0, but then becomes positive, dips down to 0, becomes positive, dips down to 0, becomes positive. So 1, 2, and 4 are still critical values, because those are places where the equation might have gone negative if these exponents were different. But in fact, the equation didn't become negative in those cases. They're still critical values because those are the only places where this particular function could have become negative if it had the same roots, but it was a little bit different.